Let me know once you see my screen. So today we are going to do chapter reading 8. Okay, it's on hypothesis testing. Let's get started. Yeah, so hypothesis testing is a framework where we are trying to validate the truthfulness of a certain hypothesis, whether to accept it or reject it, is something which we will have to do it through statistical analysis. Now, where is this used? So, in finance, for instance, one of the most popular hypotheses could be uh, something like, did the daily mean of, say, a particular financial time series like Nifty 50 uh, return anything other than zero? So that becomes my null hypothesis, which is the mean return is zero. And the alternate hypothesis is something which is opposite to this. So if I say that the mean daily return was greater than zero, or mean daily return less than zero, or not equal to zero. So these are various variants of alternate hypothesis. So null hypothesis is something which we would like to prove or disprove depending on some statistical evidence. And that statistical evidence is dependent on a certain distribution which we have to choose and on our sample data. So sample data needs to be collected on which we will try to fit it over a certain distribution depending on the kind of test which we want to run. And then we will test out for the hypothesis whether to prove or disprove depending on some statistical evidence. So null hypothesis is something which has a definite value. It can be, say, mu d or mean return is zero, or we can say, okay, average annualized return of a certain mutual fund is equal to 10%. So that could be my null hypothesis also. And clearly, alternate hypothesis could be it is not 10% or greater than 10% or less than 10%. Yeah, so these are the null hypothesis formations which need to be proved or disproved. So there's a whole set of terms around statistical tests. So null hypothesis is the initial claim which we have. So in our example, we said, okay, null hypothesis is the mean daily returns of the index is equal to zero. Yeah, so that becomes your initial claim. Now, you need sample data, which is basically evidence to be presented to try and understand whether to accept or reject this null hypothesis. It's a very simple courtroom analogy. So, null hypothesis, which is the initial claim or status quo, can also be read as innocent until proven guilty, which means null hypothesis is innocent. Alternate hypothesis is similar to saying that it's guilty, which is rejection of null and acceptance of alternate. So that's a new theory which we want to prove. So our initial claim is that mean returns of an index, daily returns are zero. But the new theory could be they are different from zero. So that could be my alternate hypothesis. Significance level is basically a certain level of probability beyond which we say that there's a beyond a reasonable doubt that uh, the null hypothesis could be rejected, which means we accept the alternate and accept the guilty verdict. So that's your significance level. In terms of a distribution, how does this look like? Your significance level is nothing but the cumulative probability in the left tail. So that is your alpha. And so, for instance, if alpha is 5%, So 5% is also called as level of significance. The opposite of that, which is 1 minus alpha, is of course the probability across the right portion, which is where the null hypothesis will be accepted. And that is nothing but 1 minus alpha, also called as confidence level. So basically, this also means that we are saying with 95% probability or confidence that we are not going to reject the null hypothesis, or the verdict remains in the favor of the initial claim. But there's a 5% chance that we might uh, select guilty verdict or reject the null hypothesis and accept alternate. Yeah, so that is what it means in terms of probabilities. So that's your significance level. Nothing but probability, cumulative probability in the left tail. Uh, of course, in some distributions, like an F distribution, we look at the other side and we say, okay, it's the cumulative probability on the right tail. Okay, so it depends, but mostly we take left tailed. The verdict is statistical decision. Yeah, which means the judgment whether it's guilty or not guilty, which means choosing between H0 and HA. This is a 7-step process towards a statistical hypothesis testing. So you state the hypothesis, you select an appropriate test statistic. So whether it's a Z statistic or a T statistic or a chi-square or an F statistic. So that depends on what kind of data are we dealing with, or what kind of hypothesis are we dealing with. So we'll very soon come to what are the different tests used in finance and in financial time series. So usually when we talk about returns, we will end up using Z or T distribution. Generally, Z distribution is also used when the sample size is more than 30, and where the population variance could be known. T distribution generally used for smaller samples because it has a fatter tail. So this is a preferred distribution because the variability of a small sample could be more, the standard error could be more because n is less than 30, and hence we need to use a distribution with fatter tails. So T distribution is preferred. When we talk about testing out variances, now variances, can I say, are squares of volatility or squares of standard deviation, right? So those can be ascertained using chi-square and F-test distributions. So selecting the appropriate test statistic is important. When we are talking about returns or difference of returns, we will be using ZT majorly. And when we talk about variances, we could be using chi-square or F. Which one to use when? We are going to come to that soon. Specify the level of significance, which is alpha, which means if I'm selecting a distribution, I need to know what is the level of confidence with which I will not reject the null hypothesis, or the significance level at which I will reject the null hypothesis. So the knowledge of alpha is important for me to understand where is this cutoff level or critical level, as we call that. Then we need to state the decision rule regarding the hypothesis, collect the sample, calculate the sample statistics, and make the decision depending on how the statistic is stacking with respect to alpha. Yeah, or critical values rather, which depend on alpha. Yeah, so test statistic needs to be compared with critical values, which are dependent on alpha. And then we would need to accordingly make a decision with respect to the hypothesis. And those would then lead to a decision whether you would like to reject or accept the null hypothesis. So stating the null hypothesis is important. I've already given you example. Once again, null hypothesis could be mean return of a stock is 0 or index is 0, or it could be, say, variance of the index is equal to, say, 0.04. This could also be a null hypothesis. A null hypothesis could be returns in my portfolio are equal to the return of the index. This could also be a null hypothesis. So not necessary that the variable has to be equal to some value. We can also equate two variables, and we can say that the difference, hence the difference between the two variables under consideration is zero. So again, the difference could be set to a value, or the individual can be set to a value. Usually in finance, we look at either returns or variance, the first moment or the hypothesis testing. So that's your null hypothesis. The opposite to that will be alternate hypothesis. Now, a lot of times we would also like to understand whether we are, okay, just taking a detour here. So, so this is our distribution. Can I say there are always two tails, left and right? Now, when I write null hypothesis as mu d equal to 0, okay, that's your null hypothesis. And suppose if we want to test whether alternate is, say, not equal to 0. So in that case, not equal to 0 means, can I say either it will be greater than 0 or it will be less than 0? So hence we are looking at two directions here. And since we are looking at two directions, we are going to look at rejecting the null outside of two tails, or within the two tails rather. So either the left tail or the right tail. So this is called as a two-tailed test. So whenever I say not equal to in the alternate, which means I'm not clear with the direction, then I will use a two-tailed test. And since alpha is the total level of significance or probability in both the tails, so in that case, if it's a two-tailed test, we will have alpha by 2 as the probability in each of the left and right tails. So this is important when we try to solve sums here. And on the other hand, if we are dealing with a specific direction of alternate hypothesis, which means, suppose I say my alternate hypothesis is the daily returns of an index are greater than 0. Then in that case, we are looking at specifically testing that in the right tail because the direction is greater. Had it been less, then we would have probably gone ahead here and tested it here. Okay, so greater is tested here on the right tail, less than is tested on the left tail. And this is called as a one-tailed test. And here the entire alpha will reside in on one side of the test. So in a one-tailed test, alpha or level of significance is either into the left tail or either on the right tail, depending on the direction. Yeah, so this is the difference between a two-tailed and a one-tailed test, which is critical in terms of the alternative hypothesis testing. So what kind of where will you test for the null hypothesis? Where will you accept or reject will depend on the degree of direction, what direction, and also which distribution and what kind of tail test, two-tailed or one-tailed, depending on the direction of deviation in the null hypothesis. Second is to select the right test statistic, which is to select the evidence. So your test statistic is nothing but sample statistic minus hypothesized value divided by the standard error of the sample statistic. We know from the previous session, standard error is nothing but the standard deviation of the sampling distribution. So whatever sample statistic we have, we can create a sampling distribution of that sample statistic, and the standard deviation of that sampling distribution will be your standard error. So usually it's given by sigma divided by root n when population standard deviation is known. If it's not known, then we use the sample standard deviation and divide by root n. So that will give us standard error of the sample statistic. Okay, you need to obviously select the level of significance, which means you need to know what level of confidence are you dealing with, which means where you will not reject the null, which is lying in the body, and where will you reject the null will be inside your tail. So that's your level of significance, which is basically alpha. There's an error which is called as a type 1 error. So that is the rejection of a null hypothesis, which is actually true. Okay. Uh, let's go to this important matrix. This is quite often tested. So the best way to remember this is RATF, which means reject, accept, true, false. Now on the columns, we have null hypothesis is true, which means actually uh, the the defendant is innocent, and in the opposite to that, where H0 is false, is where actually the defendant is actually guilty. So whether the H0 is true or false is on the columns, and on the rows we have reject as the second row and accept as the first row. So your type 1 error is where you actually end up rejecting the null hypothesis when it's actually true, which means rejection is very similar to doing the opposite, which is convicting someone. Failing to reject H0 is accepting the innocence of H0, which is acquitting him or her. But rejection is convicting someone, exactly the opposite. So, type 1 error is basically you're trying to reject someone who's actually innocent. So, can I say that is wrongful conviction, similar to wrongful conviction? And that exactly is my type 1 error, which is significance level alpha. So that's my probability, which is alpha. And that is also called as a type 1 error. Yeah. So, which means that the defendant is innocent, but you're trying to convict the defendant. So that is going to happen 5% of the time. So that's your cumulative probability in, say, the left tail, if it's a one tail test. Yeah, so that's your alpha. And type 2 error is essentially you're trying to accept or acquit someone who's actually guilty, doing the opposite. So wrongful acquittal. So you're something which is false or someone who's guilty. You're actually acquitting that person who's guilty. So can I say that is wrongful acquittal? And power of a test is nothing but 1 minus the probability of a type 2 error. So that's your power of a test. So power of a test is basically dependent on the type 2 error. So that's on the next slide. Power of a test is 1 minus type 2 error. It is the probability of correctly rejecting the null hypothesis when it's false. What does that mean? Which means convicting someone when someone is guilty. So that's the power of a test. Rejecting someone when someone is guilty, or when the null hypothesis is false. So that's the power of a test, and that is nothing but 1 minus type 2 error. Yeah, so that is called as power of a test. These concepts could be tested mostly in the form of true false, or sometimes also in the form of some numericals as well. Yeah. So this is a very, very important table. I remember it as RATF from clockwise direction. So reject, acceptance, true, false, type 1, type 2 error. This needs to be absolutely learned. Any questions on this?
No, no, sir.
No, sir.
Okay, let's move on. Step 4 is to state the decision rule, which means to to first state the rule clearly that, okay, reject H0 if the test statistic is less than 1.96 minus or greater than. Now, clearly we have also seen if you are going to the left tail, that means you're basically trying to check for the direction which is on the less than sign, right? So mu d, say less than 0. So that's where I would go on to my left tail and see whether it's in my rejection area. Your level of significance is 5%. Uh, and your the null hypothesis actually is mu d not equal to 0, which leads to uh, two tests, whether it's less than 0 or greater than 0. Less than 0 will be tested on the left side. Greater than 0 is going to be tested on the right side of the distribution, right tail of the distribution. This alpha is divided equally in both the tails, so alpha by 2. In the middle region is where we will keep accepting or not rejecting null hypothesis. So this is safe area. Anytime the test statistic falls within outside the critical value, which is the boundary, where the 2.5% probability starts on either side of a two-tailed distribution. So that will be, or a two-tailed test rather. So that's where we will start rejecting the null hypothesis. So rejection area is this, and that happens when the test statistic either falls below the critical value of the left tail or beyond the critical value of the right tail. So that's my decision rule. Then I collect the sample and calculate the sample statistic, calculate the standard error. We've seen what this is already. And once we do that, we can then go on to compare the test statistic with the critical values. So whatever test statistic you have, you need to compare it with a critical value. Critical values are heavily dependent on the level of significance. So depending on the level of significance, we will be choosing or selecting the critical values or calculating them. And then there's another way in which hypothesis testing is done. So one way is you calculate test statistic, you compare it with the critical value. The other way is you compare the p-value with alpha and start rejecting any null hypothesis where p-value is less than alpha. So again, if the probability is less than the critical value, that's where we are going to reject the null hypothesis. So what is a p-value? It's a probability of obtaining a test statistic that leads to a rejection of the null hypothesis. Yeah, so if p-value is less than alpha, then we are going to reject, which means that smaller p-value, can I say, indicates stronger evidence against the null hypothesis. So as long as our probability of a strong evidence is above alpha, we are saying we are innocent, and we are saying we are not below the critical value. As soon as we say the probability is high of the strong evidence, then we say that we are rejecting. So basically, your smaller the p-value, higher is the evidence against the null hypothesis, and greater is the probability of rejecting the null hypothesis. Yeah. So this is versus p-value. So in a few sums, we could be given the p-value and we can just compare it with alpha. Very simple. If it's less, then we reject. That means we have enough evidence of rejecting the null and proving someone guilty, essentially. Right? So this is the complete framework which we have discussed. Now let's start applying this framework to various types of cases. All right. So usually a hypothesis test in financial time series can be made about population means or population variances. When we talk about population, there are three important setups. The first one is T or Z test, that is for a single population, which means, example, return of a certain stock is equal to a certain value, say 10%. So this could be set up using T test or Z test. Now, whether we use a T or a Z will depend once again on the number of sample points or the sample size and whether the variance is known or unknown. Uh, the other setup is difference in means test, in which we are going to look at two independent populations, which means, say, mu of stock 1 minus mu of stock 2, and ideally from different sectors, for instance, maybe even different geographies. So mu stock 1 minus mu stock 2, say, is equal to 0%, which means they gave equal return. That could be my null hypothesis. So that's an example of difference in means where we are dealing with two independent populations. Now the third setup is something called as paired comparisons test, wherein probably we are dealing with, say, two stocks closely linked to each other since they belong to a same sector. It's possible. So stock 1 minus stock 2 equals to, say, 0%, same sectors. That's an example of paired comparison. Another example could be that you're doing before after comparison. So maybe you're saying, okay, let's say 2020 is where there was a structural breakdown in the markets. So the wall or the return regime before COVID and post COVID was very different. So are the returns before 2020 and after 2020, is there any significant difference in, say, the annualized return? So that could be my null hypothesis. And here, can I say we are dealing with dependent populations because they're dependent on the same variable, which is the same stock return. So return before and return after, maybe a structural break, could be another example of two dependent populations. That's called as a paired comparisons test. So those are three setups for population means. For population variances, we have two setups. One is chi-square test, the other is F-test. Chi-square test is for testing the variance of a certain population, which means, say, I want to test whether the variance of Nifty 50 index is equal to 10% annualized variance. So is that true or not? So that becomes my null hypothesis. An F test could be between two populations. So here an example could be, is the variance of S&P 500 equal to variance of Nifty? Question mark. So that becomes my null hypothesis. Alternate could be they are not equal, right? So that's the example of F test, where we are testing between variances of two different populations. Yeah, so these are five important setups. And for each of these, now we will have to choose between the distributions and the test statistic as well. So your T test, Z test. So Z test is generally acceptable when the sample size is large, greater than 30, ideally. Yeah. And here the two-tailed test can be written as the null hypothesis will be mu is equal to mu 0 versus alternate will be mu not equal to mu 0, where mu 0 is a constant, please note, and mu is a variable. So that's a mean return or population return. Yeah, so we are basically trying to test if the mean is different from the hypothesized value. Now, this hypothesized value could be anything. It depends on our belief or our initial claim. I can say that, okay, year on year, Nifty is making 14% return. So that's my hypothesis. Average annualized return for Nifty 50 says 14%. So that's my null. Now I need to check if this is true or not. And that will help me set up my alternate where I say, okay, average of Nifty 50 is not equal to 14, which means it could be less or greater than. So that could be an alternate hypothesis. An example here is, are the portfolio daily returns truly non-zero? So researcher is analyzing 250 days of call option portfolio returns. The mean sample mean is 0.1%. Sample standard deviation is this. Sample size is 250. Hypothesized mean is zero because we're testing whether they are non-zero or not. So my null hypothesis will be set up as the daily returns are zero versus alternate as not equal to zero. At 5% significance, the critical values will be selected as this. See, this is, we are indifferent whether it's going to be less than or greater than zero. So this is a two-tailed test. In a two-tailed test, we're going to divide our level of significance equally in both parts. So since here we have taken 5%, in each of the tail, we will be taking 2.5% each. And ultimately, how do we get this critical value? So if you remember, last time we had done simulations, right, in which I had taught you that you can look at a cumulative density function CDF, which starts from 0, goes to 1. On the y-axis are the cumulative probabilities 0 to 1. And on the x-axis will be the z-value. So if I know the probability, cumulative probability, and if I invert it using the standard normal distribution, norms inverse, I can find the z-value corresponding. So that's exactly what is happening here. 2.5% is the cumulative probability in the left tail. So this value is nothing but 2.5% or 0.025. And if I invert that, and the corresponding z value which I get is this value. So that can be very easily performed in Excel. We've done that in the last session. That's using norms inverse of 2.5%. And you get this as the critical value. This is symmetric. So whatever you have on the left will be the same on the right. In the case of a z distribution, it's a normal distribution, right? Standard normal distribution. So it's symmetrical. So your critical values will be just plus minus 1.96. We calculate the test statistic here, and that will be set up as how? So the test statistic here will be set up as equal to, so test stat, T stat is nothing but your sample mean, which is 0.1%, minus hypothesized, which is 0, and divided by the standard error. Yeah, standard error is nothing but your sample standard deviation divided by the sample size root n. So this is the formula. Once again, it's nothing but sample mean minus hypothesized mean divided by standard error of the sampling distribution, which is in our case 0.25% divided by root of 250. So that's how we get the test stat. Here it is coming out to be 6.33. Clearly, it lies way above the critical value on the right tail, at the right tail, and hence, can I say this value goes into the right tail, far into the right tail, which means we will reject the null hypothesis, which means they are truly non-zero. Yeah, because our hypothesis was equal to zero. So now we are choosing the alternate, rejecting the null and choosing the alternate, saying that they are truly non-zero. Okay, so this is a simple example. Another setup is where we are trying to test for the difference between means. And here an example will be average values of two independent populations different from each other. So this could be, say, return of fund one, and this could be return of fund two. where fund 1 and fund 2 are independent funds. Maybe one is a large cap fund, the other is a mid cap fund, or maybe one is a pharma sectoral theme fund, the other is a metal sectoral theme fund. Okay. Different funds which are managed differently, maybe not tracking the same benchmark. So that's probably a better example of independent returns. And the null is set up as they are not equal to zero or non-zero. The difference is non-zero. I'll just like to go to the slide which calls out for the actual formula. Yeah. So when we are talking, so here we're talking about differences between sample means of independent populations. So how do you set up the test statistic for this or calculate test statistic? So that's calculated using this formula in which we are saying it's the difference between the two samples minus the hypothesized difference between the populations, difference in the population means, divided by SP square divided by N1 plus SP square divided by N2, where SP is nothing but the SP square is the variance of the combined thing, and that is N1 minus 1, which is basically your degrees of freedom of the first sample, plus N2 minus 1, which is degrees of freedom of the second sample, divided by the total degrees of freedom, which is df1 plus df2. So degrees of freedom are usually n minus 1 because one degree of freedom is lost in computing the mean. So when you compute variance, for instance, formula for variance is xi minus x bar whole square divided by n. So to compute variance, can I say you first need to calculate the sample mean? So 1 degree of freedom is lost there. And hence we say degrees of freedom are n minus 1 for a sample variance. If it's population, then obviously n is large and then n minus 1 is not very different from n. But in a sample variance where x bar itself or the population mean is not known, we first need to calculate the sample mean. So you lose 1 degree of freedom there. So the degrees of freedom become n minus 1. So that's the exact formula which we are trying to use here. So SP square will be degrees of freedom of the first samples into S1 square plus degrees of freedom of second sample into S2 square divided by df1 plus df2. So that becomes your formula and the formula for the T stat for difference of means of independent samples. Please note, this is for independent samples. Okay. Next. So here is an example. So do abnormal returns differ for horizontal versus vertical mergers, two different kind of mergers. So they have given the mean returns, the standard deviations. We need to calculate the test statistic with respect to this formula, which I showed you. So in this formula, we need to know what is x1 bar. We need to know what is x2 bar. We need to know what is mu1 minus mu2. And apart from that, we also need to know what are the sample sizes and what are the sample standard deviations. So in this problem, we know everything, mu1, sigma S1, mu2, S2. We know degrees of freedom and we can go ahead and calculate. And also the hypothesized mean, difference of means is 0. So that's what we will substitute here in the formula. Okay, and then it's just a simple substitution of values and you can calculate what is your T statistic, test statistic. Yeah, so this is using the T values here, T distribution. So critical t values we will find. How to find the critical t values? Again, it's the inverse of the t distribution. So in the case of Z, we were using norms inverse. Here we will be using for t, we'll be using t dist inverse. Okay, so just the inverse so that we find what is the critical value here. And since t distribution again is symmetric, whatever is on the negative side will be the same critical value on the positive side. So critical values we can find from alpha. Again, this is a two-tailed test. That's how it is set up, the alternate hypothesis, which means alpha by 2 is divided into the two tails. So a critical value here, the t critical will be based on probability of 2.5% in the left tail. You invert that probability and you get the t value, which is critical value. Now, whatever test statistic you compute, you compare with the t value. Here, we are getting it as minus 5.74, which is way beyond in the left tail. And hence, that again is in the rejection region since it's below the critical value. So we are rejecting that the null is true and we're accepting that the return difference is indeed non-zero between the two merger types. Now, this is important paired comparison test. This is to test the mean difference of two dependent samples. Usually, we usually have this in before and after situations or scenarios. I gave you an example of COVID, which was a shock before and after. Another example could be a stock's beta before or after an event. So suppose that a company announced its quarterly results. So what was the beta a month before the company announced results, and what is the beta after the company announced results? So there again, you're talking about the same stock, but then there's an event which breaks it into two different regimes for the same stock. So it's a dependent sample. Or when pairs of observations are affected by a common factor. So that's the other way where samples are not independent. For instance, two firms which have very similar business models and they are from the same industry over the same period of time. Yeah. So TCS, Infosys, very similar business models, right? Or you take any other two, companies from the same industry which basically have very similar business models. So that could be an example of uh, difference of means between two dependent samples. So this is how the null hypothesis is set up, and the alternate could be not equal to zero. So here we are trying to compare the beta of a company before and after the deregulation. So did company stock betas change after industry deregulation? So maybe we are talking about a stock which related to a certain sector which was deregulated, and we are trying to compare the betas before and after deregulation. So before dereg, after dereg. Okay. So clearly two different regimes, and we are trying to compare the beta values here. So how does this test stat look like for dependent? So this is for paired comparison. So this is how the test stat looks like. So for paired comparisons test, the t statistic is used, which means again we fall back to t distribution with n minus 1 degrees of freedom. And this is how it looks. So d bar is the sample mean difference, where di is nothing but the difference between the ith pair of observation. So each pair of observations, so for instance, observation 1, sample 1, sample 2. So the difference of these two needs to be computed, and that is your di. So this is d1. Similarly, we keep doing this across all the observations, and that is basically your di. Standard error of the difference is SD divided by root of n. And what is SD? SD is nothing but sample standard deviation. So you calculate all the differences, calculate the average of that, average of all DIs over n, and you use that in this formula and then calculate sample standard deviation. Here we are using n minus 1 degrees of freedom. And then we go on to calculate the standard error, which is S d bar, which is the denominator here. Yeah. So this is how we calculate the T stat or T statistic for paired comparisons test. Please note here we'll have to create a new column of DI, which is differences, calculate the standard deviation of these differences, use that into your standard error formula. Okay, and this is the example which we were looking at here. Okay, so a sample of 39 companies was taken comparing beta before and after deregulation. So does beta change if industry is deregulated? So degrees of freedom is R n minus 1, 38, right? And you can compute the test statistic, which is basically over a two-tailed test here. So hypothesis, null hypothesis is the difference is zero, no average change in beta of the stock before and after deregulation. Alternate is that there is a difference, which means not equal to zero. So no direction specified. So we use two-tailed test. Alpha is 5%. So we again divide 2.5% to each tail. We find the critical t value. Once again, using the same approach. Again, t value, critical value will be dependent on n also, right? Degrees of freedom. So whenever we are submitting our T inverse or calculating the T critical value, we also need to supply the degrees of freedom, which is n minus 1. So which is why we keep getting different test statistics. In the previous example, we had a different T stat. Here we have a different one because it's dependent on the degrees of freedom. Here we have calculated test stat as 10.26 using our data set, and clearly that is above the positive critical value. So it lies in the rejection region in the right tail, and hence we will reject null and we will accept the alternate stating that there is a significant difference of stock betas before and after deregulation. Now coming to, so we've completed three setups for returns. Last two setups will be for variances. Is the variance of my population different from a specific value? So null could be this and alternate could be sigma square not equal to sigma 0 square. Please note this sigma 0 is a constant, but sigma square is a variable. Example, this could be an index variance or a stock variance, and we're trying to test it whether index or stock variance or maybe VIX variance is equal to say some value 10% square, yeah, or 0.01. So this is possible using a chi-square test. So chi-square distribution looks like this. It is an asymmetrical distribution. Its values cannot take a negative value. And again, there are two critical values here for a two-tailed test, which are not symmetrical. So here you will arrive at two critical values, which will not be the same. It will not be minus and plus. They will be two different values and two different positive values because this distribution is plotted above zero. So an example could be we are hypothesizing if a fund's advertised volatility still hold true. So suppose that we are saying it's a high return equity fund and it advertises standard deviation as 4%. So we need to test for this. So we test not the standard deviation, we test its variance, which is square of standard deviation. So we are testing if sigma square is equal to 0.0016. So that becomes my null hypothesis. We are taking a sample size here of 24. So the degrees of freedom is n minus 1. And say the measured standard deviation is 3.8%. So we will have to use the test statistic for chi-square. How does that look like? Let's look at an example here. So this is the chi-square test statistic, wherein this is the formula n minus 1 into s square divided by sigma 0 square. Now, what are these? Sigma 0 is nothing but the hypothesized value for the population variance. In our example, can I say hypothesized variance is nothing but what is advertised by the fund? 4%. That is standard deviations, 4% square. So this sigma square becomes 0.0016 or 0.04 square. Then there is a measured standard deviation of the sample. So that becomes your sample variance, S square. So that in our case is 3.8% square because this is standard deviation. So this will become 0.038 square. And so that's your S square. N in this case are 24 values. So n minus 1 degrees of freedom here will be 23. And that will fetch you chi square n minus 1. And then we can find the chi square values. So this is an example table where we will be able to find the probability in the right tail. For instance, here the degrees of freedom say, for instance, if the degrees of freedom were 10 and we are trying to find the probability in the right tail as say 0.95. So can I say that this value and this value will be the two critical values, 0.95 and 0.05. So we'll have to take pairs and then we will have to select two critical values from this chi-square table. So in our example, here we have 23 as the degrees of freedom, and we are going to calculate the test statistic depending on these values. In this case, the test stat, which is basically a chi-square value, is going to be equal to n minus 1 s square divided by sigma 0 square. So n minus 1 is 23 into s square, which is your sample standard deviation square, is, can I say, 3.8 percent square, so 0.038 square, and divided by hypothesized variance, which is 0.04 square. So square of 4% standard deviation of the hypothesized value. And this will set up the test stat, which is calculated as 20.76. And then we will check that against the critical values. So at 5% significance level with degrees of freedom 23, the critical values are these and these at 5% and 95%. So these will be marked here. And then we will try to see where the test stat is. So clearly it's in the non-rejection or acceptance area. So here we are not going to reject the null, and hence we're going to accept the null and say that the fund's advertised volatility of 4% holds true. So they're correct in their advertised standard deviation. So this is an example where we are testing for the vol risk, whether that holds true at a certain level. And the last setup is where the variances of two independent populations, are they equal or not? So here we are saying the null hypothesis will be sigma 1 square is equal to sigma 2 square. Equality of two variances of two normally distributed and independent populations. So that's the assumption to be taken here. So here it could be index 1 variance, index 2 variance, are they equal or not? And the alternate could be they are not equal. The test stat, which is here will follow the F statistic, is a simple ratio of two sample variances. So here it's very simple, S1 square divided by S2 square. So that becomes our comparison of two sample variances using the F test. And the F test will be dependent on the degrees of freedom. And for the two samples, there will be different degrees of freedom. It will depend on the level of significance, which is alpha. And based on that, we can find the F critical value. So for F critical value in that table, so one dimension will be df1, the other dimension will be df2, and there will be a table for different level of significance. So this there will be a table for zero point 0.05, there will be a table for zero point 0.01, and the intersection is basically your F critical value. So there'll be different tables for different levels of significance, and the intersection of df1, df2 will fetch you the F critical value. In this case, it's 1.94. So here the context or the example is the earnings volatility different for textile and paper industry? So two industries volatilities are getting compared. So directly, we will not compare standard deviation. We'll compare their variances and use the F test. So hypothesis is both are equal. Critical value is at alpha significance level of 5%. Critical value we can find using the table as 1.94. The test statistic, how did we get this? It's S1 square divided by S2 square. And we got that as this value. And can I say that's below the critical value? And hence we will fail to reject H0, which means the earnings volatility are similar for textile and paper industries. So they are not significantly different, or they are similar. And this is the whole decision tree. So if you're asked a research question, are you testing a mean or a variance? If you're testing a mean, then you're going to ask whether it's one population or two. If it's one, then you'll use a T or a Z. If there are two, then you'll ask whether it's independent or dependent. If it's independent, we'll use difference in means test. If it's dependent, we'll use paired comparisons test, where we will use the DI concept, difference in the sample points. Uh, if on the other hand, we are testing variance, then we are going to look at, we need to ask whether we are testing variance of one sample or variances of two samples. If it's one, we're going to use chi-square test, which looks like this. Otherwise, we're going to use the F test for equality of variances of two different samples. So this is the entire chapter on hypothesis testing. We don't have time to do the numericals. In the next session, I will do the numericals, and we will look at some challenging questions as well. Anything you guys would like to ask on this?
Yes, sir.
Yes.
Sir, is there a reason we are always taking equality in the null hypothesis, like for every test, like difference in means and t-test, the inequalities are always going into the alternate hypothesis. So
Yeah.
can I take the inequality like one mean is greater than the other, or my mean is greater than a certain value in the null hypothesis?
Usually we don't do that. The null hypothesis is where the initial claim is that it's equal to a certain value, and then you try to reject that claim. See,
Yeah.
hypothetically, you can take null as your claim. Your claim could also be that my returns are greater than zero. That could also be a claim. But typically, theoretically, the way we set up is the way I've told you. Yeah.
Okay. Yeah. Like, is there a certain reason, or is just like common practice?
I mean, I think it's one of the fundamental ways in which hypothesis testing is done. So it's like you present a baseline and then you are trying to uh, reject that baseline by saying, okay, whether it's greater than, suppose if my null hypothesis is mu is equal to zero, then my alternate will be greater than zero, less than 0, not equal to 0. So alternate can take various forms, right? Now, if I start with h0 as say mu greater than 0, then my maneuverance in my alternate hypothesis is difficult, right?
But sir, you still
And
have options
also,
like,
yeah, and
sorry.
also, see, null hypothesis, when I say it's true, can I say I'm
Mhm.
talking about the acceptance region? So I'm starting somewhere here. And then depending on where the alternate is, I'm either shifting to this side or this side, or maybe both I'm trying to test if you're not clear of the direction.
Right.
So that's how it's set up simplistically. So that the null hypothesis provides us a precise value or a baseline, which can then be tested in the alternate, whether it's greater, less than, or not equal to. Yeah.
Yeah.
Also, you can disprove equality, right? So it's easier to disprove equality. So when I set up null hypothesis as mu equal to 0, I can disprove this by saying, okay, not equal to 0, greater than or less than. It might not be so straightforward to disprove a null hypothesis, which is mu greater than 0.
Okay, sir.
Yeah. So
Yeah.
those could be some of the reasons why we always take equality. At least in financial theory, we take equality always. Yeah. And I've given you some of the statistical reasons why they generally take equality in the null. Yeah.
Yeah. Okay, sir.
Okay. Any other question?
No, sir.
Okay. All right. Fantastic. The other reason, okay, one more reason which I can think of is when we talk about the test stat, right? Uh, Test statistic. We are using the test statistic, some formula, right? Like we use, okay, mu minus hypothesized mean divided by standard error. Now, if in the null, if I say mu greater than 0 in the null, right? Now, the question is, it's difficult to take a specific value, right? When there's equality, I can take that specific value of mu equal to 0. I
Yeah,
can put
right.
that here. But if I write mu greater than 0, then what will I put here? So mu greater than 0, mu could be 1%, it could be 10%. So what do I put in the test stats? So it's difficult to calculate the test stat in the first place, right? When there's ambiguity. So hence we start with something which is concrete, which helps us establish a baseline through which a proper test stat can be calculated. And then we can test whether our test statistic goes into the rejection regions or not. So this is another reason why that's how it's set up, the null hypothesis as an equality, so that we can properly calculate the t stat, test stat in the first place. Makes sense, right?
Yes, sir.
Okay. All right. So next time we'll do some sums. There are some very typically uh, challenging questions which are asked from this chapter. This is a very important chapter. Okay. Uh, some new non-numericals are also asked, have been asked in the past from this chapter, which could be challenging. So we'll look at some of those typical varieties in the next session, and then we'll go to the next reading. Yeah. All right. No further questions. We'll close today's session. Thank you, guys.
Thank you, sir.
Bye bye. Good night.
Thank you,
Thank
sir.
you.